Welcome to the AI for Technical Writers podcast, where we help you get smarter than your competition. This is episode 116. I'm Fred.
And I'm Daphne. Great to be here. We're going to walk you through something pretty fundamental today, a huge shift in infrastructure.
That's right. And it's one that, frankly, is going to impact almost, every piece of technical documentation you might write about AI and data centers going forward.
It really is. We're looking at a recent article today from our producer, Curt Robbins, a senior technical writer himself. It's called, "Will Nuclear SMRs Power Our AI Future?"
Yeah, and, for our listeners, tech writers, IT pros, you might hear nuclear and think, okay, that's like way outside my lane. Deep policy stuff, maybe.
Right, but we promise you, understanding the actual physical power limits, the electricity grid itself, that's becoming maybe the most important thing to grasp before you document the next generation of LLMs.
It sounds counterintuitive, but it makes sense.
Yeah. It does. So our goal here is really to connect these pieces for you. We all use these amazing generative AI tools, right? We document the software, the APIs, the workflows that use these large language models.
Sure, daily.
But we absolutely have to get our heads around the physical constraints, the real world limits. The AI future, it isn't really limited by code anymore. It's limited by watts, by electricity.
But the infrastructure can't power the computation. The software just sits there, basically.
Exactly. The software becomes kind of irrelevant if you can't run it reliably.
Okay, so let's dig in. Section 1, the AI power crisis. We talk a lot about the AI revolution, obviously, but maybe not enough about its incredible thirst for electricity. It's staggering.
That's absolutely the place to start. The whole paradigm for power demand in data centers, it's completely flipped. Think about the legacy systems, the ones we're sort of used to dealing with.
Right.
A traditional data center rack might pull, 15, maybe 20 kilowatts? That's kind of standard historically.
Okay, standard stuff. So what happens when you start packing those racks with GPUs? The hardware needed for training these massive AI models.
Well, you don't just add a few kilowatts. That's the thing. You blow right past that. You're suddenly talking 80, maybe 100, sometimes even 150 kilowatts or more per rack.
Wow, okay. That's not just incremental. That's a different beast entirely.
It's a completely different beast, and it creates these huge downstream problems, right? It's not just the electricity bill, although that's part of it. You immediately hit physical limits. How do you cool that rack?
Right, the heat must be intense.
Intense. Then there's fire suppression and just the basic ability of the local grid, the utility company, to actually deliver that much power consistently to one building.
That's fascinating. So the documentation we might write for, say, HVAC systems in a data center, or even physical site maintenance,
Yeah.
it's suddenly way out of date because the thermal load is so different.
Precisely. And the urgency is real. Look at the projections. Global data center power demand could jump something like 165% by 2030. And almost all of that increase, it's being driven purely by this AI build-out.
That explains why you hear people like Microsoft CEO Satya Nadella saying, energy supply is the single biggest bottleneck for AI, not algorithms, not data. Energy.
He's talking about power lines and utility contracts, essentially, not code. And you see Oracle's Larry Ellison is also incredibly focused on this energy problem, too. It's become priority number one.
Okay, so if energy is the bottleneck, the obvious question is, why can't we just build more solar farms, more wind turbines? Aren't those the cleaner options anyway?
Well, it comes down to reliability. That's the key word here.
Yeah.
AI training, and even running the models once they're trained inference, it demands power 2-core 7365, rock solid, constant, reliable power, what the energy industry calls baseload power.
Baseload, meaning the minimum power needed all the time, nonstop.
Think about it. If you're running an LLM training job that costs millions of dollars and takes weeks to complete, you absolutely cannot afford for the power to dip for even an hour because the sun set or the wind died down.
Okay. So the calculation gets ruined. You have to start over potentially. That's disastrous.
It's completely unacceptable from a business perspective. So
Wow.
Conventional renewables, while super important for sustainability, they are intermittent by nature. They just can't provide that guaranteed nonstop flow that massive AI computation requires.
And this reliability issue, this intensity,
Yeah.
it's forced the tech industry to look seriously at nuclear power.
It really has. But interestingly, they aren't really looking at the kind of massive, sprawling nuclear plants we think of from the 20th century, the gigawatt scale ones with huge cooling towers.
Right. Which brings us neatly to the next part. The specific technology they are betting on, small modular reactors, SMRs.
Exactly. SMRs seem almost tailor-made for what the tech industry needs right now. They're, well, smaller, obviously.
Hence the name.
Huh, right. Their power output is typically in the range of 50 to maybe 300 megawatts, which is actually a really good scale for powering a large data center campus or even a few campuses.
Okay, so the size fits the need better.
Yes, and they're modular. Plus, and this is critical, they're designed to be less expensive and much faster to build and deploy compared to the traditional nuclear giants.
That speed and reliability must be huge factors. But I imagine safety is also a major selling point, especially if you're talking about putting a reactor potentially close to a data center.
Oh, absolutely paramount. And that's where SMRs have some really interesting design features. Most of them use advanced, what are called passive safety systems.
Passive safety, what does that mean exactly?
So traditional reactors often rely on complex active systems, pumps, valves, backup generators, external power, all working together to circulate coolant and prevent overheating.
And if those active systems fail or lose external power, like in Fukushima, that's when you run into trouble, right?
Precisely, that's the failure point. But many SMR designs are fundamentally different. They're engineered so that the laws of physics themselves, things like gravity, natural convection, the properties of the materials like molten salt or liquid metal coolants, automatically work to stabilize the reactor and remove heat without needing those complex external systems or power.
Okay, so it's inherently self-stabilizing. It fails safe, essentially.
That's the idea. It makes a severe meltdown scenario virtually impossible, as the designers say, because you're not relying on pumps that can fail or power that can be cut off. Physics takes over.
Wow, that has massive implications for, well, for the documentation, right?
Hmm.
Regulatory documents, safety procedures, less complex failure modes probably mean less complex procedures to write.
That's a key insight for technical writers, absolutely. And it connects to another point, the construction. SMR components are largely built in a factory environment, standardized modules.
Like building blocks.
Kind of, yeah. They're manufactured under controlled conditions and then assembled on site. This dramatically changes the whole construction timeline. You move away from these decade-long, budget-busting mega projects.
Which must be music to the ears of any IT project manager trying to plan a data center rollout. Predictable power delivery timelines.
It's gold, and they scale really well. A company could start with, say, one 50 milliW SMR module for its current needs.
And then just add another module later if their AI compute demand grows.
Exactly. Bolt on another one. It offers flexibility that traditional plants just don't have.
And the small physical footprint you mentioned earlier that allows them to be sited differently too, doesn't it?
Yeah.
You mentioned behind the meter.
Yes. This is really important. Behind the meter means the power source, the SMR, is located directly on the same site as the load, in this case, the data center campus. It's basically private power generation.
So it's not pulling power from the main grid.
It might still be connected for backup, but the primary power comes directly from the onset SMR, the big benefit. You eliminate transmission losses, the electricity that gets wasted just traveling over miles and miles of power lines.
So it's more efficient.
Much more efficient, and it gives the data center operator complete control over their power supply, guaranteeing that crucial reliability we talked about. They effectively become their own utility.
Okay, this is where it gets really interesting because this isn't just theory anymore, is it? Section 3. Tech giants are actually doing this. They're going nuclear. This is happening now.
Absolutely. It's not science fiction for 2040. Google, for instance, they made the first big move. A world-first deal, really.
What did it do?
They signed an agreement with an SMR startup called Kairos Power. The plan is to commission and buy all the power output from up to 7 Kairos reactors. That's about 500 megawatts total.
7 reactors, just for Google.
Just for Google's data centers. The first plant is slated for Tennessee, aiming to be operational by 2030, specifically built to provide clean, reliable baseload power for their huge data center operations in that region. That's a massive commitment.
No kidding. Okay, what about Microsoft? They're huge in AI, too.
Microsoft is tackling it from, well, a couple of angles. First, they signaled their long-term strategy very clearly. They actually hired a principal program manager for nuclear technology.
A dedicated nuclear person inside Microsoft.
Yep. Their job is basically to figure out and drive Microsoft's future SMR deployment strategy, but they also have huge power needs right now for their current AI push.
So what are they doing in the short term?
Well, get this. They signed a deal with Constellation Energy. The deal involves Constellation providing nuclear power, partly by helping to restart one of the generating units at 3 Mile Island in Pennsylvania.
Wait, the 3 Mile Island? the site of the famous accident.
The very same. Now, it's a different unit, obviously, and safety standards are vastly different today, but the symbolism is powerful, isn't it?
It absolutely is. When a tech giant like Microsoft sees its AI power needs as so urgent that bringing a historically sensitive nuclear site like TMI back into play is part of the solution.
Wow, it screams urgency. It tells you everything you need to know about how critical this power issue has become for them.
Okay, so Google's building new SMRs. Microsoft is using existing nuclear and planning for SMRs. What about the really, really big projects? I remember hearing about OpenAI's plans. Stargate.
Ah, yes, Stargate. It's reportedly backed by some heavy hitters like Oracle, SoftBank. The scale is just astronomical.
How big are we talking?
The estimates floating around are for a $500 billion AI infrastructure project. And the power requirement, 10 gigawatts.
10 gigawatts. That's, I mean, how much is that?
Okay, perspective. 10 gigawatts is roughly the output of 10 large traditional nuclear power plants, or enough electricity to power something like 7 million homes. It's enormous.
Mind-boggling. You absolutely cannot power that from the existing grid, can you?
No way. That's the whole point. A 10 gigawatt baseload power need. You can't meet that with regional utility deals or a few solar farms here and there. It fundamentally requires a dedicated, massive, non-intermittent power solution.
Which points directly back to advanced nuclear, likely SMRs deployed at an unprecedented scale.
Exactly. For a project like Stargate, the power plan is the infrastructure plan. They're inseparable.
Okay, this is a lot to take in. Let's take a brief break for a special message from our producer, Curt Robbins.
Hi, this is Curt Robbins. First, thanks for listening. I truly appreciate your support. I want to let you know that I'm currently accepting new clients. My rates are affordable, and I have more than 25 years of experience working for enterprise companies like Microsoft, Northrop Grumman, Oracle, PNC Bank, FedEx, USAA, and Wells Fargo, among many others. If you want to improve your IT documentation and communications, hire me. I deliver fast, know how to use AI to improve efficiency and accuracy, and love going the extra mile to satisfy my clients. Thank you for subscribing and listening. Back to you, Daphne and Fred.
Welcome back to the AI for Technical Writers podcast.
All right, before the break, we covered the massive power crunch facing AI, how SMRs offer a potential solution, and the fact that giants like Google, Microsoft, and potentially OpenAI are already moving fast into nuclear.
Right, so now let's really bring it home. Section 4. Why does any of this matter to you, the listener, the technical writer, the doc specialist, the IT pro? Why should you care about reactor physics or utility contracts?
Yeah, let's connect those dots.
Okay, the big takeaway here, I think, is profound. Energy strategy, grid limitations, power generation technology. These things are now becoming deeply, deeply intertwined with how we implement AI at scale.
It's not just a background issue anymore.
Not at all. The success of this whole AI future we talk about, it depends less and less on just the next software algorithm breakthrough. It depends more and more on solving this fundamental physical power problem.
Which means the job of the IT department, and by extension, the technical writers supporting them, it's changing fundamentally.
Absolutely. You're not just dealing with, AWS service configurations or cloud security policies anymore. Well, you are. But now you might also be dealing with documentation related to on-premise proprietary power generation.
We're moving from documenting purely software-defined infrastructure
to documenting physically defined infrastructure, including the power source itself. Think about what that means for IT departments. They'll need to understand SMR site planning, operational procedures, safety protocols specific to having a reactor nearby.
And someone needs to write all that down, right? New standard operating procedures, policy statement.
Exactly. New SOPs dealing with proprietary power, localized safety zones, maybe even interfacing with the reactor's control systems in some way.
Can you give us a really concrete example, like what specific documentation deliverable might change because Google decides to put an SMR next to its data center?
Okay, think about the software that manages the AI workloads, the job scheduler. Now, imagine that scheduler needs to interact with the power source.
How so?
Maybe the SMR has different operational states or output levels or even planned maintenance windows like refueling. The AI scheduler might need to know this. So you, as a technical writer, might find yourself documenting a new proprietary API.
An API for the power plant.
Yeah. An API that lets the AI scheduler query the reactor's status, maybe throttle back certain non-critical jobs if the reactor's output is temporarily reduced, or prioritize jobs based on power availability in a way you could never do with the main grid.
Whoa. Okay, that's a completely new documentation domain. You're writing specs for power consumption APIs.
Exactly. It moves the writer much further upstream, doesn't it? You're not just documenting the software's features, you're documenting its interaction with the core physical infrastructure and its constraints.
What about compliance? We're used to documenting things like SOC2 or ISO 27001 for security. What happens when nuclear regulation enters the picture?
That's another huge one. Because these SMRs might be sited behind the meter on the tech company's campus, the IT department's responsibilities suddenly expand.
How?
Well, their physical security policies, their disaster recovery plans, their compliance manuals, they now have to integrate requirements that intersect with nuclear safety regulations. Rules set by bodies like the Nuclear Regulatory Commission, the NRC in the U.S.
So IT documentation suddenly absorbs this massive new layer of regulatory burden tied to physical nuclear safety. That's a big shift.
It's huge. You're documenting failure modes that go way beyond a server crashing or a network switch failing. You're potentially documenting responses to incidents involving the power source itself.
So understanding the basics of how, say, a molten salt reactor differs from a traditional pressurized water reactor, that stops being trivia.
It stops being trivia and starts becoming essential background knowledge. It helps you anticipate the kinds of new procedures and documentation that will be needed, maybe even before the engineering teams fully realize it. You go from writing config guides to potentially drafting critical infrastructure policies.
This knowledge really does seem crucial, then, for career growth in this field, if you understand these power constraints and solutions.
You position yourself way ahead of the curve. You show that you understand the entire stack, from the physical atoms generating the power right up to the digital bits running the AI models.
If you're aiming for roles like information architect or policy documentation specialist within a major tech company doing AI, this seems like key knowledge.
I'd say it's probably the fastest way to differentiate yourself right now. The people who grasp the energy limits and the nuclear solution, they're going to be the ones writing the essential SOPs and policies for this next era.
Okay, wrapping up then, here's a final provocative thought for you, our listeners, to chew on. Building on what we've discussed, if tech companies really do start deploying their own SMRs behind the meter, we know specialized APIs are coming. We know SOPs will change.
Right.
But what entirely new kinds of documentation might emerge? Think about standards or policy statements needed to govern the complex relationship environmentally, operationally, safely between a private tech campus and its dedicated nuclear power module.
That intersection. Physical nuclear safety, localized private regulation, interfacing with complex digital infrastructure.
Well,
that really is the next frontier for technical communication in this space, isn't it?
right.
Those policies and standards will need to be written, and soon.
Something to think about. Thank you for listening to the AI for Technical Writers podcast from Curt Robbins, where we help you get smarter than your competition. Remember to like, subscribe, comment, and share. We'll see you next time.